So each of our 4 satellites have now traveled more than 10 million kilometers on orbit. They have hundreds of millions more to go. They're going to go from geostationary transfer orbit up to GEO, which is a circularized orbit. And in order to get there, our GNC team is going to lead the way. GNC stands for Guidance, Navigation, and Control, and they basically have 2 jobs. First, they have to point the satellite the right way, and second, they have to help it maneuver between orbits. So in this video, you'll get to meet the GNC team, the actual people who are doing this for our satellites in the sky, and they'll tell you all about the sensors, the actuators, and the algorithms that get us from here to there.
It is very important to know where we are in space, and we do that using attitude determination and orbit determination. So attitude determination basically tells us where the satellite is pointing. The sensors that we're using is the star tracker. In this case, we have 2 on our satellite. The star tracker is basically a camera. The camera takes pictures of the sky, and then the computer compares the picture taken with a map of the stars, and this way it's able to determine where we're looking at. And our satellites have 10 sun sensors, and this is really important because we want to point our solar arrays to the sun as much as we can, because we want to keep our satellites power positive. And lastly, gyros help us understand the angular velocity of the satellite, so how fast we are rotating in the inertial space. And for orbit determination, we are using measurements that we take from ground stations or ground entities. Those are usually ranging and angle measurements that we take and blend into our GNC algorithms, and we get the best estimate of the orbit. And we have to do that all the time because the orbit changes.
And the reason that's constantly changing is because we are commanding the satellite to move, either to change its orbit or to repoint. The things that do those movements for the satellite are called actuators.
We currently have 5 satellites in space. All of them have the same sets of actuators. So we have 2 different kinds of thrusters on our satellites. The monoprop thrusters are a single propellant system which passes hydrazine over a catalyst, which helps it decompose, and then that creates like a thrust coming out the other side. And we have an EP thruster, which is an electric propulsion system, which we use for most of orbit rays. So essentially it works by ionizing electric particles and shooting them out the back of the spacecraft, which creates impulse and allows us to thrust. So while thrusters are great for changing our orbit, they're not as good or practical to use for pointing and controlling our orientation. That's where something like reaction wheels are much better. The reaction wheels we use for 3-axis pointing. For example, like if you're holding a drill and you spin that drill, like your hand's gonna wanna spin the opposite direction. If you were in space and you did the same thing, you'd entirely end up spinning the other direction because you'd be trading angular momentum with the drill, and so it would create a torque on you. So in our spacecraft, we have 4 reaction wheels, and we stack them in a pyramid in order to ensure redundancy and also control about each of the 3 axes. So in any control system, it's super important to model your actuators well. So in simulations, we try to build models that match the way our reaction wheels work in practice. Same for our thrusters, and we try to model all manners of behavior, how they spin up, how they slow down, how long the thrusters take to heat up, how that ramp looks like. And we use all those in simulations alongside our real flight software in order to try to create as real a system we can and also simulate the real dynamics and physics of what's going on.
But of course, that's way easier said than done. When your satellites are actually up there and you're actually operating something on orbit, you have to make sure that not only are your maneuvers safe, but also that they're efficient. Safe meaning that even if something goes wrong, the satellite's going to be happy and power positive and you're not going to lose it. But efficient meaning that in order to get where you're going, you're not burning a ton of unnecessary prop. So in order to do this, we of course have to do tons of simulation on the ground to find out what's the right algorithm to run that can get us from here to there the best. And we have lots of different spacecraft modes, which are basically like settings or priorities, meaning we tell the spacecraft to please prioritize this, and then it does it in the most efficient and safest way possible.
Our satellites have a lot of different modes, starting from uncontrolled mode, meaning the vehicle is just tumbling, or something more favorable, like our TTC sun pointing mode, which is totally 3-axis stabilized, and we keep our radios pointed at the Earth, in addition to pointing the solar arrays at the sun, so we always have perfectly charged batteries and are fully powered. I think my favorite mode is the EP maneuver mode, just because we have like these 3 constraints: pointing the thrusters, pointing the radios, and pointing the solar arrays at the same time. And doing that is very challenging, in addition to avoiding like sun occlusions that come into play there. So it's just a great engineering feat of making that work. There are several different simulation scenarios that we go through. So speaking about perigee passages, staying inside our geo slot. To cover all these mission phases, we use Monte Carlo campaigns. What Monte Carlo means is that you take one mission phase and you simulate it hundreds upon hundreds of times. You try to replicate all possible scenarios that you could encounter when you reach that mission phase. And what that does is it ensures that our software executes robustly and perfectly in all kinds of situations that we might encounter.
We've gone tens of millions of kilometers with hundreds of millions more to go. But because of the GNC team and these sensors and actuators and algorithms, we have faith that they're going to go just as well as they did for the first part of the journey.